Hello. Good afternoon, everyone. I'm Kabir Tomer, and I'm going to be presenting on cryptography from quantum one-wayness, which is joint work with Akshita Khurana from UIUC. Now, modern cryptography began with some breakthrough results constructing public key encryption with schemes such as RSA and the Diffie-Hellman key exchange. And these schemes were also some of the first schemes that were proven to be secure. And their proof of security relied on assuming that certain specific number theoretic problems were hard. And the downside of building schemes based on the security of such specific number theoretic problems is what happens if one or more of these hardness assumptions turns out to be false. Well, this fear leads to what is possibly one of the central goals of theoretical cryptography, which is we want to base our primitives on the weakest possible complexity assumption. Well, weakest possible because we want to minimize the chance that our assumption doesn't hold, and complexity assumption because these assumptions tend to be pretty simple and weak, while also being easily instantiable from a variety of concrete problems. Now, in the classical setting at least, this idea of what is the minimal weakest assumption, this is pretty much solved. There is a simple search problem called a one-way function, which is necessary for all classical cryptography. And what is a one-way function? A one-way function is a function that can be efficiently computed for all points on its domain, but is difficult to invert in the average case, which is to say for a random y, it is hard to come up with an x such that y is equal to f of x. Now, once we add quantum computing to the mix, the situation is a bit different. And that is because using quantum resources, we can relax or even remove some assumptions. And the most famous example of this is quantum key distribution, and which is possible information theoretically without the need for any computational assumptions at all. Now, the case of QKD is more of an exception than the norm because several central and important cryptographic primitives like bit commitments and multi-party computation do require some kind of computational hardness assumption. However, there's a recent line of work that shows that those hardness assumptions can potentially be weaker than one-way function. And now that we can potentially get quantum cryptography from assumptions weaker than one-way function, this leads very naturally to the open question, what are the assumptions that are minimally necessary for quantum cryptography? And there are roughly two major candidate assumptions for this, for the crown of being the minimal assumption. And those are something called one-way state generators and something called EFI pairs. And our work is about the relationship between these two objects. So I will define them shortly. A one-way state generator can be thought of as a quantum analog of a one-way function. So it consists of two efficient algorithms. One is a key generation algorithm, which samples a random classical key k. And then there's the state gen, which takes this randomly sampled classical key k and outputs or maps it to a quantum state phi of k. And the security property we want here is that this state gen algorithm should be computationally infeasible to invert. And what that means is given polynomially many copies of phi of k, should be hard to find some key k prime such that phi k and phi k prime have some noticeable overlap. And note that the state gen cannot simply be a unitary because otherwise it would be trivial to invert. There needs to be some kind of a measurement step or some junk state that is hidden. Now, EFI pairs, on the other hand, they can be thought of as quantum commitments stripped to their essentials. And for those unfamiliar with quantum commitments, they are a cryptographic primitive that allow you to commit to a bit, and in such a way that the bit is not visible to anyone who receives the commitment. However, you cannot later go back and claim that you committed to a different bit. And EFI pairs are a pair of efficiently sampleable quantum states, rho 0 and rho 1, that are number one, far in trace distance, and number two, computationally indistinguishable. And being here computationally indistinguishable means that there does not exist any efficient algorithm that can distinguish rho 0 from rho 1. And the name EFI pair actually stands for these properties: efficiently sampleable, far, and indistinguishable. Now I'll situate these assumptions in their context by taking a look at the landscape of quantum cryptography in general. And the reason these are these leading candidates is because most quantum cryptography primitives end up implying one or the other of these two objects. Like digital signatures and quantum money variants imply one-way state generators. EFI pairs happen to be equivalent to commitments to zero knowledge for NP or QMA and secure multi-party computation. And one-way functions and pseudo-random state generators imply both of these objects. But the gap in our understanding here is what is the relationship between these two objects. And our work here aims to shed some light in this relationship by showing that one-way state generators with pure state outputs imply EFI pairs. And the consequences of this is, since most things end up implying EFI pairs, we can reasonably place EFI pairs as the leading candidate for quantum minimal assumption. Now, our results can be split into two parts. The first part is showing that pure one-way state generators imply a natural search problem with classical instances that is called a one-way puzzle. And the other part is showing that these one-way puzzles can be used to build EFI pairs or equivalently quantum commitments. And in interest of time, I will mostly be focusing on the first part because it is conceptually simple, and we think that one-way puzzles are interesting in their own right. But the bulk of our technical contribution actually involves the second part, which has many more ideas that we won't really be able to touch on in this talk. Now, before we dive into our techniques, I want to first show something that doesn't work, which is to say I want to show how some classical techniques that are used to build EFI or commitments from one-way functions do not work when we translate them into the quantum setting. And I want to show what kind of barriers we run into. Specifically, suppose we are given an injective one-way function f. Now we want to build an EFI or a commitment from this one-way function. So the Goldreich-Levin theorem gives a simple hash function such that for a randomly sampled x, f of x together with the Goldreich-Levin hash of x is computationally indistinguishable from f of x together with a random bit. And this is even when we are given the hash key for the Goldreich-Levin hash. Now, we want to build EFI, which, as the name says, have to be far and indistinguishable. So if these two distributions are our candidate EFI states, we get indistinguishability. We just need to show that they are statistically far. And the way we show that, here at least, is because f of x is injective, then f of x basically determines its preimage x, which in turn determines the hash of x. While in the second distribution, since this last bit is sampled randomly and is no way determined by f of x, it is clear to see that these distributions have some statistical distance. Now, what happens if our function is no longer injective? Well, if it is no longer injective, then f of x does not necessarily determine this hash, which means these distributions are no longer necessarily far. And the way past this problem, which was given 25 years ago in this breakthrough work by Hastad, Impagliazzo, Levy, and Lubin, which I'll refer to as Hill, is to make this function f of x look more like an injective one-way function. We can't make it completely injective, but we can make it behave more like an injective one-way function. And the idea is to append a pairwise independent hash of the input x that we call h of x. And now, f of x, h of x should determine the preimage x with sufficient probability. Not perfectly, but with some good enough probability. And crucially, the length of this hash will depend on the number of preimages of f of x. Now, the reason for this is if f of x has many preimages, then we need to output a longer hash so that that hash, together with the function, can fix a particular preimage. But if it has too few preimages and we end up hashing too much, then this indistinguishability relation that we're still relying on will start to break down. So we need to know what is the number of preimages, and our hash length depends on the number of preimages. And this is at least the idea of how we build EFI from one-way functions. The actual construction is a lot more complicated, but this is what we are going with right now. And the goal here is we want to translate this to the quantum setting, which is we want to build EFI from one-way state generators. Now, as I said, one-way state generators are a quantum analog of one-way functions. So what happens if we just try to replace the one-way function output in the construction with just the output phi of x of the one-way state generator. Well, the indistinguishability part seems to work out. And now, because the one-way state generator may not be injective, we still need to append the hash of x to make it behave more injective. And this is where we run into a problem. Because the length of a hash of x will depend on the number of preimages of phi, this causes an issue in the quantum setting, which is it is not always clear what does and does not count as a preimage in the quantum setting. So consider the following situation. We have a key x1 and a key x2. These are classical keys. And they're classical keys such that their state generator outputs map to these states which have some noticeable overlap. So they're not very close, but they're not very far either. So the question is, does x1 count as a preimage of phi x2? Well, we would want to say no because these states are still somewhat far, but it is not so easy to just discard that because we need to define preimages in a way that accurately captures what the uncertainty in the key is given the key output. And this x1 is still part of the uncertainty. So this partial overlap problem means that we cannot clearly define preimages. So a natural approach is to try to get rid of these preimages. Try to get rid of these partial overlaps. And a natural approach for doing that is, well, here we just have a single copy of the state, so there is some overlap. What if we took multiple copies of this state? And as we take multiple copies of the state, it is true that this overlap goes down and these states end up almost orthogonal. This unfortunately doesn't quite work. And the reason for that is, although states that when we take a single copy have this partial overlap end up close to orthogonal, states that were formerly very close, which could almost be treated as the same state, once we take multiple copies, they may end up in this partial overlap setting. So taking multiple copies, it is not clear how to make it work. So we think of trying a different approach. Now note that this partial overlap problem doesn't happen with classical strings. And that is because classical strings are either identical or they're just orthogonal. There is no partial overlap notion. So an idea is to map a phi of x or some number of copies of phi of x to a classical description as x, such that the classical description still hides x. Now, the issue is that n-qubit quantum states cannot have efficient classical representations in general. But luckily, in this technique, in this setting, there are still some things we can do. Specifically, we rely on efficient shadow tomography and the algorithm given by Huang, King, and Preskill, which I will give a simplified version of. And the simplified version is, it consists of an efficient algorithm called shadows, which takes in order n copies of a pure state phi, pure state psi. And it maps shadows these pure states psi to a classical string S, which is in some way a description of phi. And this string we call the shadow of phi. And while this description does not completely capture all properties of phi, one thing that we can do with this description is we can use it to estimate the overlap between psi and any state phi x. And this overlap will have some constant error. And this estimation process will also be inefficient. However, this estimation process will work for all keys, and that is the crucial part. So now returning back to our EFI construction, we will try to apply shadows to this state phi x or copies of phi x. And instead of phi x in our construction, we will use this computed shadow of x. And what happens when you do this is the output becomes classical, so no more partial overlaps, while inversion still remains computationally infeasible. And this is true because the shadows procedure is efficient, and also because the estimation procedure works for all x. These are both crucial. Now, the object that we get when we apply shadows to this state phi x is a simple search problem with classical outputs called a one-way puzzle that we will now define. And a one-way puzzle consists of an efficient generation algorithm which samples pairs of keys and puzzles. And it also consists of a potentially unbounded verification algorithm that checks validity of key puzzle pairs. And the property we have is any efficiently sampled key puzzle pair will be accepted by the verification algorithm. However, given just a puzzle, it is hard to find any key that verifies for that puzzle. So it still has some kind of one-wayness. And I will note here that in the literature, this verification algorithm has been treated as efficient, and here we allow it to be unbounded. Now, we claim that one-way puzzles in this form are interesting in their own right. And the reason for that is they, in some sense, model a quantum process that samples hard problems along with their solutions. And our results show that any such process will also imply commitments in EFI. Another interesting thing is one-way puzzles are, or we show them to be minimal for the hybrid cryptography setting. And this setting is a setting where algorithms for cryptography are quantum, but the outputs are all classical. And we also show that one-way puzzles, or rather, we believe that one-way puzzles have implications for separation results, and there has been some follow-up work on this already, but we will not go into much detail there. Now, one-way puzzles solve our overlap problem, but there's still a lot to go through, still to get to EFI pairs or quantum commitments. And in interest of time, I will not be covering it in detail, so we will just get a taste of some of those problems. If this is interesting to you, I would highly encourage that you look at our paper where we have a more thorough overview. But anyway, so to see what the barrier is, let us consider again the case of one-way functions. And in the case of one-way functions specifically, let us consider some keys x1, x2, x3, x4 that all happen to map to y under this one-way function, to the same value y. So f of x1 equals f of x2 equals f of x3, all equals y. Now, when this key is sampled uniformly at random, then what is the pre-image distribution or the distribution on keys induced conditioned on the output being y? So we sample a key and the output is y. What was the distribution induced on pre-images? So if the output is y, then each of these pre-images is equally likely to have been sampled. So this is because the key is sampled uniformly at random, and all keys that do not map to y have zero probability of being random. So what we end up with is a distribution that has equal probability on all the pre-images and zero probability on all other keys. And this is called a flat distribution. And it turns out that the techniques from Hill crucially rely on flat distributions in order to go through. We need a flat distribution in order to hash enough so that f of x hash of x in some way determines x without breaking this indistinguishability relation. The problem when we switch to one-way puzzles is because the key puzzle sampling algorithm is just some arbitrary quantum algorithm, the pre-image distribution may in general be very far from flat. It may not look anything like a uniform distribution at all. And in this setting, Hill doesn't necessarily apply, because if we try to hash enough so that the shadow of x and the hash of x fix the pre-image x, this indistinguishability relation will break down. So this non-flatness, I will stress here, is a pretty major barrier in building cryptography from one-way state generators. And specifically, we believe it is the main challenge when trying to build pseudo-random objects from one-way state generators or quantum one-wayness in general. Now, in this particular setting, we have something of a way out, which is we note that any distribution, even one that is very far from flat, will have some noticeable subset that is close to flat, so that the distribution over this subset is pretty close to flat. Now, we call this subset a good slice or the good subset. And the idea is, in our second distribution, instead of always appending a random bit, when x belongs to the, when x is not in our good slice, we make sure that the distributions are identical. We continue using the Goldreich-Levin hash. But if x is in our good slice, in our well-behaved slice, we replace it with a random bit. So instead of it being a random bit always, it is a random bit only when we are in the good slice. And now, because this good slice is pretty well behaved, we do manage to get statistical distance and computational indistinguishability. But this introduces new problems. And the new problem is that it is not efficient to determine whether or not x is in this good slice G. which means that this second distribution is no longer efficient to sample, which is a requirement for EFI. And we need many more ideas to get past this. Brief highlights. We need to hash a lot more cleverly in order to get not just statistical distance, but actually a gap in entropy in the two distributions. And we also need to use flavor swapping for quantum commitments in order to later amplify some weak security properties that we are able to get. In summary, we develop a quantum variant of Hill that still works for arbitrary pre-image distributions, and we build on it to get EFIs or commitments. And the conclusion then is that one-way state generators imply, or one-way state generators with pure outputs imply EFI pairs through this classical output object called one-way puzzles. And as a result, we can reasonably place EFI pairs as the minimal assumption for quantum cryptography. And a few things that are not on this slide, but I would like to stress. One-way state generators are also interesting in the sense that we believe that they're an interesting intermediate object when trying to build cryptography from meta-complexity reductions. And also that just building cryptography from this search to, from a search problem is in itself interesting and requires interesting techniques. Now, there are some open problems in this domain, and many, in fact. One is that we require this restriction on pure outputs. So can this be relaxed? Can we build EFI states from just mixed state output one-way state generators? Another open problem is, can we use one-way state generators using similar techniques to actually get pseudo-random objects, which is something that we can do classically, but we don't know how to do in this quantum setting. Another problem is whether this implication holds in the reverse direction, whether EFI pairs imply one-way state generators. And also this hybrid cryptography setting, where outputs are classical, algorithms are quantum. We show that all of those cryptographic primitives imply one-way puzzles, but we don't know whether one-way puzzles themselves can be used to build primitives in the hybrid cryptography setting. And that is all from me. Thank you very much for listening.
So one question is, so this hybrid cryptography means interactive one. So if this
Sorry?
so this hybrid cryptography means interactive one, because
Yes.
if this is non-interactive,
it is interactive, but the outputs are classical.
Okay. And so in that case, why you think that one-way puzzle imply hybrid cryptography? So because one-way puzzle doesn't have any efficient verification.
Yeah, that is the essential problem. You are right. So we don't know whether it's possible, but we don't see any clear way.
Okay. And another question is, so from one-way puzzle, you construct EFI pairs, and that EFI pair is classical EFI pair, which means just a classical mixture of computers.
So it would be, but there is, so we get non-uniform classical EFI pairs. It requires some non-uniform parameter at every step. And classically, the Hill construction also has some intermediate object which has non-uniform parameters, but they're able to remove non-uniformity because they get pseudo-randomness. They can stretch and then do some combiners. Those techniques don't work because of the flatness issue. So we have to do flavor swapping and some other interesting things. And those things, I think, make the construction inherently quantum. So we don't quite get just classical EFI. Yeah, so but that is a hope, maybe.
Yeah, so at least so you can also construct a classical input, classical output quantum evaluation one-way function with auxiliary input, because EFID imply one-way function.
So you say that again? I didn't follow you.
Yeah. So this, if this EFI output of EFI is just a mixture of classical bit stream.
Yeah.
In this case, I think EFID imply one-way function. So so this means now you also get classical input to classical output quantum evaluation one-way function.
Yeah. So maybe then it is not possible to get it purely quantum. Because in our case, it is not. The output is not. Sorry, purely classical. In our case, the output is not purely classical.
Hi, sorry, maybe I'm a bit confused. So, how does the noisy storage model fit into this picture?
Sorry, the noisy storage model?
Yeah.
Is that something I mentioned, or is that something separate?
No. So just what people assume, right, quite often, right, when you do bit commitment, right, they do
yes.
noisy storage model, right? So where is this in this picture, and how do you see this fit in them?
So, I mean, this can be contended, but generally all these cryptographic primitives assume perfect quantum storage. So even EFI pairs implying commitments has them sending some quantum state and saying that you maintain this quantum state for arbitrary amount of time while we have some entanglement between us. So I'm not sure, like this. Maybe I don't understand your question.
But if people consider noisy storage model, I mean, so it's outside this picture. I'm trying to understand what this means.
Sorry, I'm not sure I follow.
Well, maybe we can take remaining questions after this session, but let's thank Kabir again.